Hello, hello. My name is Maxim Jenihin, an associate professor at TalTech, Estonia, leading a research team on trustworthy and efficient computing hardware, and also coordinating a European twinning project, TAICHIP. And today here with me, Professor Yanjing Li from the University of Chicago in the United States. She's an expert in robust system design. Welcome, Yanjing.
Thank you. Thank you, Maxim. Thank you for having me.
And also joining her is Professor Luciano from Loughborough University in the United Kingdom, who is an expert in embedded systems reliability, focusing on issues like radiation-induced soft errors.
Thank you for having me as well. It's a pleasure to be here.
This podcast episode is a part of TAICHIP research project, a European collaboration focused on developing energy-efficient and reliable chips. And I would like to start with remembering one quote from IBM, which is approximately as old as I am. So back at the time, it was said that a computer can never be held accountable. Therefore, a computer must never take or must never make a management decision. Right, and today, what we see from self-driving cars to smartwatches, we are all surrounded by intelligent devices which actually make decisions for us. And definitely, we don't want them to malfunction. So among other things, what we can do to make these intelligent devices which surround us and to make them more trustworthy is to enhance their reliability against hardware faults. And these days, one of the most interesting topics which is being discussed in our community is actually the failures which are called silent data corruption. So, Yanjing, could you explain this phenomenon in simple terms?
Yeah, I can try to do that. I think silent data corruptions they're basically like a particular type of very dangerous hardware failures. Usually, if you have hardware failures, right, in the past, I think people assume that there will be fail stop. So some things would crash, right, or something like that. So you'll notice that there's actually a problem happening in the hardware level. But this type of hardware failures that we refer to as silent data corruptions, they are very hidden in a way that they don't cause any visible symptoms in a system level, but instead they cause like some incorrect computation. So for example, if we want a computer to compute 1 + 1, it may tell us the answer is 3, and then you would move on to another computation, right? So at the end, you'll get incorrect results, but if the user is not checking or there's no other mechanism to check the correctness of the program, you won't know about it. So the program will finish as if it's correct, but you'll never be able to figure out that the answer is actually incorrect. So that's why we call it silent, right? That's why it's called silent data corruption. And that's a simple example, but in data centers that we have today, including places like Google and Meta, they have reported that they have seen this type of silent data corruptions in their data center operations. So for example, in Meta, they have this example where at some point they found that a bunch of files got deleted in their databases for no reason. Like those files should not be deleted, but they just disappear. And then in the end, they figure out that it's because of a silent data corruption issue. When they're calculating the file sizes, some of the non-empty files are getting a size of 0 for some reason, and that's why they got deleted by mistake. So these are real examples of silent data corruptions.
Okay, but then I heard that the main source for SDCs, silent data corruptions, is actually radiation-induced soft errors. And maybe, Luciano, could you help us to understand why and when we should care about cosmic rays coming from the sun and sometimes even from somewhere behind the sun?
So this is a really interesting topic, because when you stop and think, we are here at sea level, and why should we consider that kind of error? Would that affect us on a day-based life? In fact, the answer is it true? Yes, that can affect our day life, because every single electronic device nowadays can suffer for that kind of bit variation. So in order to make it simple to understand, a radiation particle that can come from some can basically change a bit from 0 to 1. And at the end of the day, that can change the computation that a single device, our mobile device, when you look at autonomous vehicles, that can affect a given computation that is critical to the operation of such kind of device. For instance, people are discussing, we have like object detection that has been embedded inside of a car. So such kind of computation is devoted to identify people crossing the street. And if a radiation particle move or change the value of a bit to 0 to 1 or vice versa, so that might lead to a wrong detection, and then our automatic car might do not detect a person and something badly can happen. So we are exposed that to at sea level, and that can happen not only to data centers, but to critical device like an autonomous vehicle, for instance.
But you mentioned sea level, so does this altitude matter somehow?
Exactly, it's a really good point. Not only the altitude, but also where we are located geographically speaking. So some countries, when if you think about the Titicaca altitude, so some automated boats, they can be more exposed to radiation, for instance. When you look at drones, when you look at the altitude, for instance, usually in the UK, in the US, drones can fly to up to 400 feet. And we are exposed to a certain level of radiation effects there. But when you start to think that we have nowadays power solar drones flying at 6,000 feet, so the exposure, the energy radiation where those devices are exposed is 20, 40 times higher. And so we must have proper mechanism to reduce the vulnerability of those devices.
So the further we go, the less is a layer of the atmosphere which...
The higher we are, the more radiation particles our device is exposed to.
Okay, but I think that for silent data corruptions and similar dangerous failures that we have for reliability, we also have other sources, other types of faults and defects. Could any of you elaborate a little bit on these other sources?
Yeah, sure. Maybe I can start. So other than soft errors, which actually have been a problem, right? We know that it's a big problem for a long time. There are other sources, like Maxime, you mentioned. So one of the most surprising ones perhaps is actually manufacturing defects. So when we manufacture our chips, right, things are so small right now. The size of the transistors, which are the basic building blocks of our chips, right, they're so small. Like we're talking about somewhere around 3 nanometers now, right? And then we're going to go down even smaller. So it's very difficult to manufacture completely reliable, chips and devices and so on. So there are these defects, right? There could be opens, there could be, other kind of breach effects or, things like that. The details doesn't matter, right? But it results in basically wrong values being produced or computed again. And this is mainly from manufacturing. And in the past, we believed that, we have manufacturing testing, which would screen for these defects, right? And we would trust that this kind of, testing mechanisms would make sure that whatever chips that are actually deployed in the field would be free of these defects. But in data centers, they have found that to not be the case, and they have observed substantial test escapes, which are basically defects that escaped manufacturing testing, and then they got exposed to the field. So a lot of this silent data corruption, mechanisms that were now observed in data centers, I think a major source of the reason why these hardware failures are happening are because of these manufacturing defects. And I think the reason, one of the big reasons is because manufacturing testing is really facing increasing challenges. As we already mentioned, this very small size of the building blocks of our chips. And then also our systems are becoming very, very complex. So it's even more difficult to test the chips thoroughly.
Mm-hmm. So it's a kind of weak defect that when we do apply a manufacturing test, then we don't see anything wrong. But then under some particular conditions, it can still manifest and cause all these troubles.
Yeah, exactly. So that's, one very major source of silent error corruptions. And I can mention, maybe one more. So another one is what we call the aging effect. So basically, as we, use our systems, our circuits, right, they age as, our humans and other animals age. And basically what happens is that the circuits would run slower and slower. And at some point, they are slow enough where, when we're, try to capture the actual results, the results wouldn't arrive in time for the correct results, right, to be captured. And so, again, this would result in incorrect values being captured as the results of the application. And so this kind of silent error corruptions could occur.
Mm-hmm. Another example, another source of error comes from the higher temperature operation of those devices nowadays. Because we are reducing the technology that we are fabricating those components, and you are adding more and more and more transistors, more processors there. So if you look to desktops, we start with 4-core desktops. We have now 16-core desktops already. And if you look at these tiny circuits with thousands of processing elements inside, so we are developing those devices, and we are adding way more complex software stack. We are running more complicated applications, heavy applications with operating systems there, drivers, and many other things. So when you have all of that together and you start to operate for a given period of time, the higher temperature operation can, for instance, flip a bit, and that can lead to an error. And it's difficult to monitor and to check all of that at runtime because the complexity of those systems is increasing every single day. When you look to machine learning, almost every single device nowadays has some kind of machine learning running on the top of that. And those are complex kind of applications. And that definitely, in the end of the day, increase the temperature operation of our systems that can ultimately lead to an error.
Yeah, and I would add to that it's really difficult to test ahead of time this kind of conditions because it's completely workload dependent and environment dependent as well. So depending on what applications you're running at a particular time, right, on the system, depending maybe on, what's running before this application and what's after, and what your neighbor systems are working on, those can all have an effect on this kind of problem.
So we have a huge number of combinations, right, of what can happen.
Yeah, exactly.
And you cannot test all of them.
We cannot test all of them, yeah.
So we are running for more advanced architectures, for more tiny technologies. We are going for performance, but at the same time we are creating for ourselves new problems because all these solutions became very fragile at the end of the day.
Exactly.
So we have all these troubles. We have process variations related to manufacturing. We have soft errors. We have aging. So how to cope with them, what to do with them. Yanjing, I remember that our research team actually learned about your team because some years ago we started to search for frameworks to assess reliability of complex deep learning model accelerators, hardware accelerators, and then we noticed a framework called Fidelity, right? So could you elaborate on the advantages of this framework, which is well known in the research community, but also maybe other frameworks that your team is busy with?
Yeah, sure. Firstly, thank you. Thank you for being interested in our work. Let me first quickly talk about our Fidelity framework. It's basically a framework that allows us to analyze the resilience property, right, of a deep neural network, but it's targeting what we call deep learning accelerators. So these are not general purpose like CPUs, right, like we all use today, but these are really specialized hardware engines that's just target deep neural network applications. And what this framework allows us to do is to really understand if there's a hardware failure that occurs in the deep learning accelerator. How does it affect, some deep learning workloads that are running on top of it? So why is that important? It's because if we want to really understand a problem, we need a way, right, to tell us, what could really happen to the application when hardware failures occur. And that would give us insights on how to deal with them. So that's why it's really important. And especially for deep learning applications, because a lot of people would think that because deep learning itself is a stochastic kind of application, it's already error tolerant, right, in a lot of ways. So in what cases do we need to worry about it, right? And when hardware failures occur, that kind of problems a lot of people would have. So we really need a framework to tell us exactly, what happened. So Fidelity is exactly, the framework that allows us to do that. And the methodology that we use for resilience analysis is called fault injection. It's a statistical approach where we basically, during the execution of a deep neural network of interest, maybe you're running, a ResNet, or maybe you're running a transformer, right? And then we can actually inject a fault, which is, for example, we're flipping a bit from 0 to 1 on purpose into, our execution environment, and we observe how it affects the output of that neural network. And it's a statistical technique. We can't do it once, right? Because it's hardware failures, sometimes they can happen, anywhere at any time. So we need to repeat that for a large number of times. And then we can obtain the statistical understanding on what happens. Maybe, 90% of the time, the result is still correct. 10% of the time, the result would become some other label, right? Or something like that, then we basically have a way to characterize that. And there are, of course, other fault injection. This is called fault injection. And of course, there are other fault injection frameworks as well. But I would say the limitation of existing, or frameworks prior to Fidelity would be either they take a long time because we're doing fault injection in the hardware level to get very accurate results. So we're incorporating all the hardware details in a simulation. So the simulation can run extremely long. So that's, one side of the, technique. And then on the other side, we have the software level fault injection. And they can happen much faster, but they cannot capture the detailed hardware level mechanism. So the results may not be correct. So Fidelity basically overcomes the limitations by deriving very accurate software representations of hardware level failures. So we can perform our fault injection in the software level, but can still produce very accurate results. So that's the main advantage of Fidelity over existing networks or frameworks that allows us to perform resilience analysis.
Mm-hmm. And I'm sure that you are working with a number of other tools which were also somehow derived from Fidelity and continue this work. And I think that for us here in Europe, what can be an interesting question is that when you work, when you do research in the United States, right, you have the advantage of being close to these very large and well-known corporations in the computing domain, such as Intel, NVIDIA, Google, Meta, right? So do you collaborate with them? Do you have an example of collaboration? So probably for you, it should be easier to access them.
Yeah. It's actually, it is an advantage, I would say, and it's actually very necessary because we mentioned, silent error corruptions. It was actually, become like a really big problem, and everybody know about this problem because Google and Meta came out with these papers, right, that said, we're noticing that silent error corruptions are such big problems. And the industry, actually, the hyperscalers like Google and Meta and the chip vendors like Intel, NVIDIA, AMD, they actually noticed that they all agree that this is a big problem. So a lot of these companies, they actually got together and they form a working group that are aiming to address this challenge. And it's part of the what we call the Open Compute Project in the US, and they have funding for silent data corruptions. And with partnering with academic universities, basically. So very fortunately, we're one of the teams that got selected to be part of this initiative. So we have, interactions with industry and hopefully, I think funding aside, right, which is obviously important, but I would say the more important aspect is that we can actually learn from what are currently being observed in data centers, right? And what are the really real problems that we need to look into and address. And I think that is really the most attractive part of this collaboration. And one specific example, actually, it's a great thing that you mentioned fidelity before, because after this framework, we have done many studies, firstly on inference, right? Of course, because, of all the dangers that, inference workloads can give us, including the car example, right, that Luciano told us about. But we are also interested in training. And for training, deep learning training, right? It's even harder to think why hardware failure would be a problem, because training is an iterative process that's constantly updating weight values, right? So there's already like a self-recovery kind of mechanism built into that. But we really, we have this framework, so we should prove it, we think, right? So we actually did some experiments on training as well, fault injection experiments. And very quickly, actually, my student found a case where the training wouldn't converge at all because of just one single bit flip that happens just for one clock cycle. It's not even a persistent effect, but it basically corrupted the entire training process. So we started at that work, and at that time we were already talking to some of these companies like Google about our framework and some of our experiments. And we mentioned about training, and very interestingly, they also told us that they actually already noticed this kind of issues in their deep learning training kind of experiments as well. So we actually, then actually started a collaboration, and we, actually now have, a paper that's already out that's talking about how a single cycle bit flip can corrupt an entire deep learning training process. And we also have a very efficient mitigation technique learning from these experiments. So we also have a way to deal with them now.
Cool.
Yeah.
It's really cool. Luciano, I know that you work with cross-layer reliability assessment. And when we talk about cross-layers, and we mean it's from system level, system layer, maybe sometimes using even virtual platforms, and down to measures through physical irradiation of the chips. So, and also you challenge yourself to address not only these more powerful chips, such as GPUs, but low-cost, energy-efficient edge devices. So could you elaborate on your cross-layer approach, and could you also explain when tottering chips with beams of radiation particles is really necessary? So does it depend on applications? What is your take?
It's a really, really good topic. So when I started to look at the reliability of circuits in general, I started to work at RTL level. So we have like a very detailed description of each component that is part of a large system. So when you work at that level, you have a good observability, because we use also fault injection. So you flip a bit during the execution of a given application on the top, for example, of a processor. But if you want to explain that to a large amount of people to try to capture, to take the picture of that. So just at this level, just to boot a processor, an operating system running on a given processor at that detailed description, we would need a day or a few hours only to boot the operating system, to turn on the system and to have that up and running. When you start to add applications on the top of that, and you have to replicate the fault injection operation a few thousands of times at least, so you're gonna need weeks, months of simulation time. So that is unfeasible. While that provides us with a really good observability of the system, what I mean is, which would be the impact of that flipped bit on the operation of that application, so I can see whether that would propagate inside of the processor infrastructure and so on and so forth. However, it's unreasonable. We do not have the time to do all the variations and experiments at that level. So we did some experiments in our group, and then basically we started to think, okay, so let's maybe abstract some stuff away and let's work with virtual platforms. So virtual platforms are frameworks that they integrate different compilers, software stack, so we can instantiate operating systems. There are different operating systems. You can run the same C code, the same software that you run in the board, you can run on the top of models of different processors. We can consider different instruction set architectures, and that provides us with more flexibility. So at the beginning, when you look to a design space exploration, we can depart from there to have some initial idea about configuration X against configuration Y, and which one would be more reliable, I would say. So the main principle of our, like, say, narrow down design space exploration approach is, let's start the investigation using some high-level models where you can abstract things away, you can conduct more fault injection scenarios, then you can exclude not optimal solutions, let's say, and then you can narrow down and you can run some RTL simulations depending on the complexity of the system. And at some point in time, we have promoted as well, like, some hardware-based fault injection. So what we did, we have created a system where we have a few boards, all of them, they are interconnected, and we have developed a framework that allows us to distribute different fault injection campaigns at the same time. So we have a lot of boards running in parallel, and we can capture more accurate results from those fault injection campaigns, and you can still eliminate not suitable configurations of our targeted system, and then later on, you can expose that to a real radiation scenario. So answer your question, I believe that when you look at safety critical systems, at some point in time, we have to conduct real radiation experiments. At industry level, so people do that. So depending on the components that they are developing, so they go for real radiation in order to check whether that new component or new processor architecture would be more or less reliable against radiation-induced software errors. So I believe at some point in time, you cannot exclude that. We must take that into account, although that's a very costly kind of approach, but we have to do that. The difficult when you expose something, you take a board, I deploy a given operating system running, I don't know, or a given machine learning model running on the top of a given board. When exposed that to radiation, the main difficult and challenge is to be able to identify from where the error comes from. It's really, really challenging part. And there are different approaches here and there. And, that's the I believe that there is an entire community who does real radiation experiments, and we still are looking at proper ways in conduct those radiation experiments in order to have more accurate observability about what is happening when a system is running under thermal or neutral radiation.
So if you do fault injection in software, right? If you model a fault, then you have full controllability of where and when you would like this fault to occur, right? But then the way how it propagates, maybe it's a little bit inaccurate because you don't have everything exactly as it's in hardware. But in case of hardware, what we see, we cannot really control when and where the fault occurs. It's just a beam of real radiation particles which are random. But in fact, if something happens there, then the effect is real, right? Because it truly propagates through the hardware.
Exactly. So it's really difficult when we can start from a high-level description. How accurate is that? We did some measurements depending on the scale, I would say, of the application. Your accuracy goes to the roof, so you cannot really trust on the results that we are looking at. Sometimes if you can isolate some very tiny cases, we were able to check that somehow the obtained outcomes in terms of, which were the effect or the impact of a given number of fault injections. In this scenario here, we were able somehow to compare the results with a good occurrence, I would say. But mostly important thing to say here is that when we conducted some experiments using real boards, when you conduct the fault injection using the real boards, that provides us something very close to the results that we can obtain from radiation, with a higher observability than real radiation experiments. But still, the lower you go, the less observability you have, but more accurate results are there. So you need to try to find like a good trade-off on when and how to use, or in which level we're supposed to work at and to look at.
Okay.
Yeah, that's my view.
Yeah, but you have the privilege to use actual like beams, right? Hitting hitting the processor. I think it's hard to, for all the academic groups, for example, to have that kind of environment. And I think that the challenge is that, we have that, which is very good for soft errors, but for some of these other errors, right, that we mentioned, like defects or aging, like it's very difficult to do real experiments on those as well. So there's a lot of work in our community that has to, catch up in all of these aspects.
Yeah. So it's interesting that you mentioned these different privileges or approaches or the conditions that we can that we are exposed to in our research. So just a couple of days ago, we met at DATE Design, Automation and Test in Europe conference in Lyon. Right. So despite this conference is very international and they have contributions also from different continents, still you can feel spirit of European research. So Yanjing, in your opinion, what is the main difference of doing research in the United States and in Europe, where European research teams maybe are a bit lagging behind? What's your opinion?
Yeah, I would first just straightly say that I don't think that European research is lagging behind in any way. I have heard, maybe some differences in, degree requirements, maybe, or how, education are structured, or how research groups are structured, or maybe how fundings are different. So just what I heard, right? But I think as far as, the actual, technical research contributions, directions, I feel like, everywhere I go, it's a very vibrant community, like Europe, US, I think very similar in terms, that we all want to solve important problems. We all want to push, technology forward. And especially, in our community, on reliability, robust systems, and, hardware security, right? This broader community, I think it is a very vibrant, really, community, both at here and also at the US. And one thing that maybe both of us can, think a little bit is, are there some way that could promote, international collaboration a little better? I think, of course, we collaborate, but it's more common for US to collaborate together and Europe to collaborate together, but this cross-continent kind of collaboration might be a little difficult. So if there's some way that we can, bring us together closer and, collaborate easier, I think that's the direction that we all want to go towards.
That would be really nice. So still, let me poll on drawbacks or points where we are lagging behind. Luciano, with you, just a year ago, we were sitting at the same DATE conference at a panel, right? And the panel was about resiliency of deep learning accelerators. And I remember that back at the time, Professor Masoud Daneshtalab was expressing a concern that our hardware research community is not so much advanced in terms of playing with latest, largest deep learning models, and then the software community, AI community is a little bit more ahead. So did you notice any changes in the last year? Is there any progress to address this issue?
Yes. In fact, I have seen some papers around and people started to look at more robust and large-scale machine learning models. I can comment one of my partners, for instance, in the last radiation campaign that we did together, he deployed the DeepSeek on the Raspberry Pi, and he exposed that to radiation. So I know people are already looking at those large-scale transformers, large-scale machine learning models. I particularly am still looking at research-constrained device, so I'm focusing more on tiny kind of machine learning models yet. And I remember that at the time, one of the questions that we have received is that most of us, we are looking to CNN, convolutional neural network models only. And this is something that I reflect on my own as well. And I start to look to other models such as binary neural network, binarized neural network. So I started to look at more optimized models in order to be able to run them in research-constrained device, and as well to see how they would operate in a real physical hardware implementation, for instance, developing models to run in FPGA, aiming to perhaps to have them running inside of a autonomous vehicle or something like that. But definitely, I have seen a lot of papers that people started to look to more robust and complex machine learning models. This is something that's there, and I believe that's the next step. If you started to look at the future, recently, ARM has released the A312 processor that would allow us to run models with millions of parameters on the top of a CPU. So I believe this is the next step. So the architectures are evolving, and we will be able to definitely run more robust machine learning models there in tiny systems, and then we're gonna have to consider a case study larger machine learning models.
Yeah, and I would also, if I may add to that, like this problem that you are talking about, right? It's not a European problem. I think in the US too, being able to really experiment with large scale like neural networks and things like that is a problem that we have to think about. Yeah, because in our research group sometimes where it's not just yours, right? Because I know your research is on more resource-constrained devices, but I think in academic groups, our resources are constrained, all constrained, right? In some extent to no matter what systems we're studying. So yeah, it is a very important topic. And, we see a lot of the, directions in the software community heading towards large language models and, things like that. Then how do we, incorporate some of those aspects into our research, right? That's really, an important problem to think about. I think we're all lagging behind in some way.
But now, when Luciano mentioned future, right? Let's make an exercise. I'll give you an invisible crystal ball, right? And you guys will look into the future. So what would you see there, let's say, in 5 years? What kind of developments will happen to address even more, to make our computing systems that surround us even more robust, even more reliable? I don't know, who first?
Oh, this is a really good question. And try to visualize that. I might start by something that is missing, something that somehow we discussed at the panel as well, right back at date. So in order to cope and to deal with what is coming next, autonomous vehicles, they might be at every single country at some point in time. And we need to make those things more robust. That definitely is there is no way out, I believe. And we need to bring together academics and industrial partners more closely. We still do not have a well-defined, standardized set of rules on how to conduct fault injections, which are the correct level to explore X, Y, or Z. So there is still a lot of open questions there and open, spaces that we need to fill in. So we need to put people together to work, because we all know that at the industrial level, so they do tackle this problem differently. They have their own approach, and they do that on specific cases. But there is no well-defined standards to all of us. And at some point in time, you're going to need that. We have some standards for automotive in many situations. They are still debating at the time which would be the next, let's say, requirements that must be there. And robustness of the system is key. We have some requirements, some well-defined rules already, but for what is coming next, you must have something more clearly and well set and well defined. So I believe this is a key thing for what's coming next, because as I said, the architectures, the hardware, where we are, hardware accelerators for machine learning, the processors, they are getting more powerful. So they are doing that to allow us to run more complex and large scales machine learning models, probably in every single user device. At some point in time, you're going to have all of that together. And we must find a way and explore new mechanisms, maybe adaptive mechanisms, to allow us at runtime to identify a wrong functionality of the system coming from a given error I'm going to use this example of a flipped bit, and then you must be able to not only detect, but take an accurate and fast decision to tackle that on the fly. So this is something I believe you'll be there. Yeah, yeah.
Yeah, I think that's exactly my vision as well. I think our systems are only getting more complex, right? And if you have heard of this like chiplet-based systems, these are actually, we make chips. They may be, use different underlying technology. It could be not just transistors that we know of today, but other sorts of devices like photonics, right? For example, this one example, or some sort of resistive memory kind of technology. And then they can be specialized for different applications. And then all of these tiny chiplets can be integrated together using very advanced integration technology like 3D even, or 2.5D we already have today. So basically we have this like really massive, complex systems. And
also heterogeneous.
Heterogeneous, yeah, those are really heterogeneous in terms of both functionality and technology, right? But the cool thing is they can be all now integrated very closely into, a system. And the system must be very intelligent as well. Our systems today, they can do a lot, but I would say that they are not very intelligent, taking care of themselves. And if we can make the system more intelligent, right? So having the mechanism to be able to figure out, okay, there's some hardware failure, some bit flips happening, or somebody that's trying to perform some sort of security attack. If the system is able to recognize those, and then not only that, right, but take appropriate actions to figure out how to handle that, maybe recover, right, itself or repair itself, that would be, what we really need. And I would say that taking that one step further is that not only would the system be able to detect, right, maybe they can even predict. They would figure out some conditions and say that, okay, these are the conditions that could lead to, a potential problem coming down the line. So I would configure myself in a way, right, so that I can avoid these problems to begin with. And that would be, I think the dream for everybody in our community.
Looking forward.
Yeah.
Okay. So I think it's time to wrap up. Thank you both for this very insightful conversation. So that's the end of this episode. Stay curious, stay resilient, and until the next time.